Hi students, my name is T. Rashekar, working as a lecturer in Civil Engineering, SRRS Government Polytechnic Sirsila. So this subject is for the Civil Engineering final year students 5th semester, and this subject name is Reinforced Concrete Structures. Subject code C501, and we are in the introduction to RCC and principles of working stress method. So let us see the basic concepts of working stress method. Objectives: on completion of this class, the student will be able to explain the basic concepts of working stress design and explain assumptions, permissible stresses in the materials. So in the previous class we have seen the regarding the introduction of reinforced cement concrete, and we have seen the ingredients of concrete, so the materials which we are using in the RCC we have seen. So now we are going to see the methods of design in the reinforced concrete. What are the methods of design we are using? So a flow chart is described here. So the first one is working stress method. So this is the first method which was implemented in the reinforced concrete structures. And the next one, ultimate load method. So this is the another method which is used in the for the designing and calculation purposes. And third one is the limit state method. At present we are designing the structures as per the limit state method, because it is very safety and its safety guidelines are approximately very good. And next is based on experimental investigation. From working stress method, because it is uneconomical but safe. So we cannot we can design the structure, but it is uneconomical. So we cannot give the what we say assurance, but the structure will be safe. And coming to the ultimate load method, it is very economical, okay, which you are using the design. From the ultimate load method, the structure will be the very economical but failed to satisfy serviceability and durability. So here in some cases the structures which are there, they will be getting failure in the some of the conditions, some of the actual designs were not visible. So the structure will be the economical but fail due to the serviceability and durability. So in the upcoming classes we will be going to explain regarding the what is serviceability and durability. And the next, in the limit state method, it is comprehensive method. So the limit state method is the approximate method for the design of RCC structures. So let us see the working stress method, their basic concepts. So in the first one you see the conventional method based on elastic theory. And the next is stresses are within the elastic limit. So here the conventional method which is based on elastic theory, so it is the theory which is made up of on the based on conventional method. And here the second one is stresses are within the elastic limit. And the third one, permissible stress is equal to ultimate stress by factor of safety. Whereas the condition for factor of safety is equal to 3 for concrete, okay, and 1.78 for steel. So you remember this, the factor of safety in the design conditions for concrete is 3 and 1.78 for is the steel. So what is factor of safety? So factor of safety is to take care of uncertainties in estimation of working loads. So these factor of safety will be taking the care of regarding the uncertainties in the estimation of working loads, and it will be to take care of variation in material properties. So if any variation occurs in the materials just like cement, sand or any aggregates, so it can be what we say, it will be adjusted the by during the factor of safety version. And next you can see failure criteria is the stress, that is stress also will be controlled. By taking the factor of safety, here the stress can be controlled. So what are the drawbacks regarding the stress versus strain curve for concrete is assumed as linear, but it is not true. So you know the stress versus curve, strain curve. So it is coming, I will be explaining you. So the factor of safety does not predict the true margin of safety. So by taking the factor of safety, we should not give the 100% assurance that it will be not predicting the, at least that means it will be not reaching the margin of safety of a structure. And the failure criteria assumed is stress based, but strain criteria is realistic. Okay, so this is called our stress and strain. So actually what do you mean by the stress? Stress is nothing but the load by area. Okay, so what do you mean by the strain? So the strain will be described when the realistic failures will be occurring. Okay, so here the effect of creep and shrinkage of concrete is ignored. So what is creep and shrinkage here? When the creep has occurred in the concrete and the shrinkage of concrete will be ignored. So let us see the what is creep. So here a creep is a time dependent deformation due to sustained load. Okay. So what is the creep it is saying here? It is a time dependent deformation due to sustained load, and creep is indicated when strain in a solid increases with time while the stress producing the strain is kept constant. So it is known as creep. Okay, but here what are the sustained loads? So here the sustained loads which are there, what do we call the sustained loads? The sustained loads are nothing but they are the self weight of the structure. That means dead loads. The dead loads we have discussed in the previous class. So we will call it as the self weight of the structure. So when the a time dependent deformation due to sustained loads are acted, so when the creep is indicated that when the strain in a solid increases, that means the structure of the load increases with the time. So when the stress producing the strain will be the kept constant. Okay, so that is the creep here. And what is the shrinkage here? So the shrinkage is, it is a volumetric change of concrete due to moisture loss without application of any external loads. So the volumetric change, that is nothing but when the mixing of concrete, so the changes will be appeared. That means it is called the volumetric change. So when it is changes due to the moisture loss, so somewhat losses will be happening at the time of the concreting. So that is due to the moisture loss without application of any external loads. When the external loads are not acted, so this shrinkage will be appeared. So that is known as the creep and shrinkage. And here the stress is also force applied to a material. It is divided by the material's cross-sectional area. So for the stress, you can see the formula, that is it is determined as sigma is equal to P by A. So here sigma is determined as stress and P is load and A is the cross-sectional area of a structure. Okay, suppose you see the stress is acting on a beam. You can see this is the a beam type structure. Okay, so the loads are acting here. This is a force. You can see when the force is applied here, we will determine it as P. Okay, so the force are acting on the a structure, so you determine it as a x. Okay, this is determined as x. So when the loads are acted here, so it will be taking the loads pushes to the both sides. So then here the stress will be acted at the any part of the center of the portion. So this is known as the load. Okay, whatever the P, it is known as load. The two loads are acting at the point of the place. But what is the area it is acting, whether it is a circle, structure or rectangle? So this portion is called A, area. So it will be determined like this. You can see here. So that's why we will determine it is as a stress is equal to load by area. How much area it is affected and how much load was acted. So then coming to the strain, strain is the deformation or displacement of material. So what is the meaning of deformation or displacement? So it is called in the simple language change in length by original length. So suppose you can see the example regarding the strain also. So a small bar is there. So this is the L which is described here, the length of the bar. And if the load acts at the one side of the force, so when the load pushes or it extends, the bar will be changed. This portion is determined as delta L. So which is the up to L, it is known as actual length. When the changes occurred in the delta L is known as the change in length. So here the strain is described as change in length by original length. So this is also called deformation or displacement of material that results from an applied stress is called strain. So we can say change in length as compared to original length, that is before any variation. So this is called the stress and strain. So let us see the upcoming. And here this is also uneconomical section. So it is described as uneconomical section, whereas assumptions. So what are the assumptions are there? Let us see now. So assumptions as per Annexure B of IS 456-2000. So the at any cross section, plane section before bending remains plane after bending. So the structure which is there, it should be the plane section before bending and remains plane after bending. So it should be happen the any beam or any structure, they should be in a the cross section which is there. Okay, so this is the first assumption. And all tensile stresses are taken up by reinforcement and none by concrete except otherwise specifically permitted. So what are the tensile stresses which are there? In the tensile stresses which are acting on the structure, they will be taken up by the reinforcement and none by the concrete except otherwise specifically permitted. And the stress strain relationship of steel and concrete is a straight line. So the stress strain relationship of steel and concrete will be in the straight line, and the modular ratio M has the value of 280 by 3 sigma CBC. So the M is determined as modular ratio, and sigma CBC is equal to permissible compressive stress due to bending in Newton per mm square. This is determined as newtons per mm square units, permissible compressive stress. So what is the permissible stresses for concrete? So from the table 21 of IS 456-2000. So this is a table, you can see the grade of concrete which is determined. and this is the permissible stress in compression, Newton per mm square, and these are the permissible stress in bond for plain bars in tension, tau BD Newton per mm square, M15, M20, M25, M30, M35. These are all grades of concrete. And in bending sigma CBC, it is 5 Newton per mm square, 7, 8.5, 10, 11.5. And in direct bending compressive stress, sigma CC 4, 5, 6, 8, 9. And permissible bond in plain bars in tension is equal to 0.6, 0.8, 0.9, 1.0, 1.11. So this is the table we have to remember while calculating the permeable stresses for concrete. The note here, the bond stress given in column 4, so this is the column 4, shall be increased by 25% for bars in compression. So when the bars in compression, we have to increase the 25%, okay, because it is given for the plain bars. And the bond stresses for deformed bars shall be increased by 60%. So for deformed steel bars, we have to increase up to the 60%. Next is permissible stresses for steel as per table 22 IS 456/2000. So we can see serial number 1, types of stress in steel reinforcement, that is regarding tension up to 20 mm over 20 mm. The mild steel permissible stress should be 140, and for 20 mm over 130. When it's coming to the HYSD bars, we have to take 230, 230. And compression in column bars, it is 130 for mild steel and 190 for HYSD bars. And compression in beams and slabs up to 20 mm and over 20 mm, that is 140 and 130 and 190 and 190. So finally, these are the permissible stresses and permissible stresses for concrete and steel. So we have seen the permissible stresses for steel. Now let us see the modular ratio M. So what is the modular ratio definition? Ratio of modulus of elasticity of steel to modulus of elasticity of concrete. So the modular ratio of M is determined as ratio of modulus of elasticity of steel to modulus of elasticity of concrete. So that is described as M is equal to capital ES by capital EC. M is small, M is equal to capital ES by EC. S is steel, C is concrete. As per code, M is equal to 280 by 3 sigma CBC. So this is the as per the code, we will be determining the modular ratio formula. So what is sigma CBC? It is the permissible compressive bending stress in concrete. So this will be known from the table that we have discussed in the previous topic. So you can see here the concrete and M15, M20, M25, M30, M35. For M15 we have to take 18.7. For M20 grade concrete 13.3. For M25 11. For M30 9. For M35 8. Table 1. Showing values of modular ratio for different grades of concrete. So ES is 2 into 10 to the power of 5 Newton per mm square. And EC is equal to 5000 root FCK. So what is ES and EC here? Elastic modulus of steel and elastic modulus of concrete. Now based on shape, it is in the rectangular. This is a rectangular section, and T section, this is a T section. The modular ratio will be applied, and another one is L section. Next, types of beams. What are the beams are there? Let us see now. So these beams are the very important topics. So this is a plan. You can see this one is called L beam, whereas this one is called rectangular or T beam. So the L beam and rectangular beam, it is described as. So actually in this type the L beam will be there, whereas the rectangular or T beam will be in this condition. This is the actual elevation and this is called plan. So based on placement of steel, it is singly reinforced. Reinforcement is provided only in tension zone. What is singly reinforced beam here? The reinforcement will be provided only in the tension zone. So that is, you can understand by seeing the diagrams. So this is simply supported beam. You can see the bottom bars which are provided, these are in the tension zone, and in the cantilever you can see at the top portion it will be provided. Okay, so whether a simply supported, how it will be there, it will be in this type. So that's why they will keep in the bottom of the beam the loads, that is known as tensile zone. Whether it's coming to the cantilever, you can see it will be like this. So this is a cantilever beam. Here the loads will be acting at the top of the zone. This top of the portion is in the tension zone. And next is doubly reinforced. So here reinforcement is provided in both the directions. Whereas in singly reinforced it is provided only in one direction. But coming to the reinforcement provided in double reinforcement both the directions, here the tension and compression zones will be there. So we can see in the diagram the top 3 bars are provided and the bottom 3 bars are provided. So this is here, the bottom is in the tension and the top is in the compression. Important terms. Neutral axis. What is neutral axis? And it is determined as X. Definition of neutral axis, it is very important definition. It is a line formed by the intersection of neutral plane with any transverse cross section. So this neutral axis is, it is a line which is showing in the, just like a neutral plane in the between the transverse cross section. So it divides the cross section into compression and tension zone. So that we can clearly understand where the compression will be there and where the tension will be acted. So it is critically or balanced depth of neutral axis is determined as XC. So that's why we will call it as critical or balanced depth. And actual depth of neutral axis is determined as XA. So this is the actual depth of the neutral axis. So here you can see in critical neutral axis it is corresponding to a section in which the maximum stresses in both concrete and steel attain their permissible values simultaneously. So in the critical neutral axis section only this will be happen. So it will be corresponding to a section in which the maximum stresses were produced in the concrete and steel. There will the permissible stresses or will be the simultaneously. So let us see the diagram here. So it is a cross section of a beam. Okay, so you are seeing from the one side direction. So here D is determined as depth of the beam and B is determined as breadth of the beam. Okay, so NA, it is called neutral axis line. We can see the dotted line which is there. So this is the our neutral axis line. Okay, and AST is nothing but area of steel, 1 2 3 bars which are there, AST. Okay, and here the cross section of beam is there. So when the neutral axis is acting on the neutral plane, So it is determined as XC. So what is XC here? So if you see, the XC is called critical by balanced depth of neutral axis. So where is critical here? So this is a critical, okay, and this is a balanced depth. The D is determined up to here, and the total E up to the bottom of the beam, it is determined as capital D. So this capital D is overall depth of the beam. So to get the small d of overall depth of the beam minus the cover of the beam, okay, whether the covers will be for the beam 25 mm or 20 mm, and the diameter of the bar also should be minus. Then you will get the depth of the beam, that is the effective depth of the beam. So from that you can see the neutral axis acting at the bottom of the beam. And so when the this appears here, you can see the sigma CBC and sigma HT by M. This is called idealized stress strain curve. So when the load is acting on the beam, so it shares the load by in the tension zone and compression zone simultaneously. Okay, so this shows the our diagram in the stress strain curve. So we will also show it as a idealized stress strain curve diagram. Okay, so these are pointed as A, B and C, and E and F and G. The next is from the figure 6, that is from the previous figure, from similar triangles ABF and ACE. So the XC by D is equal to sigma CBC by sigma CBC plus sigma brackets close sigma ST by M. And next, critical neutral axis XC is determined as from the stress diagram XC by D is equal to sigma CBC by sigma CBC plus into sigma ST by M. So where is the sigma CBC? So this is the sigma CBC. And here what is written? Sigma ST by M. So sigma CBC by sigma CBC, the whereas in the compression and tension, plus sigma ST by is nothing but the steel, okay, whereas sigma ST is determined as what is sigma ST? So it is the compression steel it is produced here, my modular ratio. So XC is determined as small d, where K is equal to sigma CBC by sigma CBC plus sigma ST by M, where K is equal to critical neutral axis factor, and K is also a constant for given grades of concrete and steel. For M15 concrete and mild steel, sigma CBC is equal to 5 Newton per mm square and sigma ST is equal to 140 Newton per mm square. Therefore, K is equal to determined as 5 by into 5 plus 140 by 18.7. It is determined as 0.4, whereas K value is constant 0.4. Similarly, K is equal to 0.289 for M15 and for Fe415. So remember this value. Next is depth of neutral axis XA. So it can be determined by equating the moments of equivalent areas about neutral axis. So it will be determining the moments. That means in the neutral axis you can see the moments also will be acting on. Okay, these movements will be in the positive or in the negative. So equivalent area of steel in tension zone is equal to M into AST, modular ratio into area of steel. From figure 5 we can considering moments about neutral axis once we see the figure 5, so which is the diagram. So this is a figure 5 diagram. So from this if you see the moments which is acting here, P into XA into XA by 2 is equal to M into AST of D minus XA, whereas B into XA common by 2 okay is equal to M into AST D minus of XA, which is a quadratic equation in XA. By solving the above equation, XA can be determined. Next, important terms, lever arm. It is determined as Z. The symbol is determined as Z. So what is lever arm? Lever arm is the distance between tension and compression forces. So this lever arm is called, it is the distance between tension and compression forces. So you can see in the diagram, C acts as center of gravity of triangular stress block, whereas XC by 3 from top fiber. So this is from the top of the fiber, the center of gravity, the neutral axis will be there, and XC is the distance of the beam and Z is the lever arm. So this portion which is acting, it is called lever arm, and T is the tension between the lever arm, distance between the tension and compression. So Z is equal to, it is determined as D. Where is the D? So up to here the D will be there. This is called D. So D minus, where is determined K? So K is a constant value into D by 3 is equal to D into 1 minus K by 3 is equal to, it is determined as J into D, where J is equal to lever arm factor, and is determined as 1 minus K by 3. Whereas J is a constant for given grades of concrete and steel. Next, types of sections in working stress method. One is balanced section or critical section, under reinforced section, over reinforced section. Let us see the balanced section. What is called balanced section? Failure occurs in compression and tension simultaneously. So in balanced section, we can see it is in failure the tension will be occurs, whereas in the compression also. So that we can identify it is a balanced section, and XA is equal to XC. So when calculating designing problem, we will identify what is XA is equal to XC. And moment of resistance with respect to concrete is equal to moment of resistance with respect to steel. The next, stresses in concrete and steel reach their maximum permissible values simultaneously. So as we have discussed this one, stresses in concrete and steel reach their maximum permissible values simultaneously. So MRC is equal to C into lever arm. So this is the C into lever arm is determined, and MRC is equal to B into XC sigma CBC into D minus XC by 3 by 2. This is the moment resistance, and MR moment resistance of tension is equal to T into lever arm, or MRT is equal to AST sigma ST into D minus XC by 3. So these are the balanced section formulas, where C is equal to total compression, and T is equal to total tension. So in balanced section, it is the critical percentage of steel is MRP is equal to MRC. Therefore, AST into sigma ST into D minus XC by 3 is equal to B into XC plus into sigma CBC D minus XC by 3 by 2. So the formula we have to remember. Therefore, AST sigma ST is equal to B into XC sigma CBC. AST by BD is equal to XC into sigma CBC by sigma ST by D. AST by BD into 100 is equal to XCD into sigma CBC by sigma ST into 100. Whereas AST by BD into 100 is equal to defined as PT. It is known as critical percentage of steel. Next one is under reinforced section. So it is occurs when the failure occurs in tension. So XA is less than XC, that is AST you are less than AST ball. So AST is nothing but under reinforced. So which is under reinforced section is less than AST balanced section. Therefore, actual stress in concrete is less than permissible stress. So moment of resistance MR is equal to sigma ST into AST into T minus XA by 3. So this is the formula for the moment of resistance determined. So MR under reinforced is less than MR under reinforced is less than MR balanced section. So next one is over reinforced section. So first one we have seen balanced, second under reinforced, now the third one is over reinforced. So it failure occurs in compression. Here the XA is greater than XC. That means the compression is greater than steel. So AST over is greater than AST balanced. That is AST over reinforced is greater than AST balanced. Actual stress in concrete reaches maximum permissible value first. So this will be treatment in the stresses concrete. So here moment of resistance of over reinforced section is greater than moment of resistance balanced section. So that means we are having the three types of sections: balanced, under reinforced section, over reinforced section. So these are all the sections which are used in the design of RCC structures. Mainly the field method which is used here in the sections will be determined. So this is very important, these formulas. Moment of resistance is upcoming in upcoming topics. So under reinforced section is safe, but over reinforced section is not safe. So under reinforced section, if gets safe, it will be constructed, but over reinforced or any other failures occurs, we have to reconstruct. So that's why we have to check the whether the structure is in the safe condition or not. That is depending upon the construction process. So let us stop here. So we have seen these topics now. So finally summary, in this class we have learnt about modular ratio. M is equal to 280 by 3 sigma Vc, and neutral axis, that is critical XC, actual XA, lever arm Z, types of sections, and under reinforced, over reinforced, balanced. So these are the three types of sections are there. So totally these are the topics of the first chapter. and these are very important topics. So I hope everyone have understood. Thank you. Have a nice day.